Hello, my name is Sergey Nosov. Today we're diving into knowledge graphs, a technology that's becoming increasingly important in the AI and data engineering space. You've probably interacted with knowledge graphs without realizing it. Every time you see those information boxes on the right side of Google search results, or when Siri answers factual questions about famous people, you're seeing knowledge graphs in action. For those of you working with large language models, knowledge graphs offer something really exciting. They can give LLMs persistent memory. We'll explore how that works and why it matters. Let's start with a simple example you see on screen. Einstein was born in Ulm. This might seem trivial, but representing facts in this structured way opens up powerful possibilities for AI systems. Here is what we'll cover in the next 15 minutes. We'll start with the fundamentals. What exactly is a knowledge graph? And how do nodes and edges work? Then we'll explore how they integrate with natural language processing. And most importantly for many of you, how they can solve the memory problem that plagues current LLMs. We'll look at real examples from Google, Microsoft, and Meta, then wrap up with practical guidance on how you can start building with knowledge graphs yourself. I promise we'll balance theory with real-world applications. This isn't just academic, it's technology you can use today. So, what exactly is a knowledge graph? At its core, it's a directed, labeled graph that represents facts about the world. Think of it as a way to model knowledge the same way your brain might, through connections and relationships. The key components are nodes and edges. Nodes represent entities. These could be people like Einstein, places like Paris, or even abstract concepts. Edges represent the relationships between these entities. The critical insight is that every piece of information is stored in what we call a triple: a subject, predicate, and object. Looking at our example, Paris is the subject, capital of is the predicate, and France is the object. This might seem simple, but it's incredibly powerful. Unlike traditional databases where you might have separate tables for cities and countries, here the relationship is explicitly modeled and queryable. You can ask questions like, what are all the capital cities? Or, which cities are in France? And the graph structure makes these queries natural and efficient. The labeled part is crucial. These aren't just random connections. Each relationship type has well-defined semantics, meaning the graph knows what capital of means in a way that enables reasoning. Let's dig deeper into the building blocks. Nodes can represent anything: people, companies, books, even abstract concepts like artificial intelligence or democracy. Each node has a type label, like person, Einstein, or city, Paris, and can carry properties like birth dates, population, or founding year. Edges are where the magic happens. They're not just connections. They're typed relationships with their own properties. A born-in relationship might have a date property, or a friend of relationship might have a since date indicating when friendship began. Looking at our examples here, we can see how these connect. Einstein was born in Ulm in 1879, and he wrote the book Relativity. Notice how we can traverse paths. If we wanted to find all books written by people born in Germany, we could follow these connections. The ontology or schema aspect is important for larger systems. Rather than having a free-for-all where anyone can create any relationship, successful knowledge graphs define their entity types and relationship types upfront. This ensures consistency and enables more sophisticated reasoning. Here's where things get really interesting for software developers. Knowledge graphs and natural language processing have a powerful bidirectional relationship. First, we can build knowledge graphs from text using NLP, natural language processing. Named entity recognition identifies entities in sentences. When it sees Albert Einstein and Ulm in a biography, it knows these are entities worth capturing. Relation extraction then identifies that Einstein was born in Ulm, represents a born-in relationship. Entity resolution is crucial here. When the text later refers to Einstein, he, or the physicist, the system needs to link all these mentions to the same entity node to avoid creating duplicates. But the real power comes when we flip this around. Once you have a knowledge graph, it dramatically improves NLP tasks. The classic example is disambiguation. When you see the word apple in text, is it the fruit or the company? A knowledge graph provides context. If the surrounding text mentions stock price or iPhone, the graph helps route that to Apple Inc. Question answering becomes incredibly robust. Instead of keyword matching, you can traverse relationships. Which movies did Christopher Nolan direct? Becomes a graph traversal problem. Find the Christopher Nolan node, follow all the directed edges, and return those movie nodes. This creates a virtuous cycle where text helps build better graphs, and graphs enable better text understanding. Now, let's tackle the big question for AI developers. Why should you care about knowledge graphs when working with LLMs? The fundamental problem is memory. LLMs have finite context windows. Even the largest models can only remember the last few thousand tokens of conversation. They can't recall what you told them yesterday or even earlier in a long conversation. This severely limits their usefulness as assistants or agents. Knowledge graphs solve this by providing external, persistent memory. As your LLM application runs, it can extract facts from conversations and store them as triples in a graph database. Over time, this builds up a comprehensive knowledge base about users, projects, preferences, and relationships. The beauty is in the retrieval. When generating responses, the LLM can query the knowledge graph to fetch relevant facts. If someone asks, "What's my project deadline?" the system doesn't need to search through conversation history. It queries the graph for edges connected to that user and projects. Looking at our example, imagine a personal assistant that remembered Alice prefers lattes and has a web app project due March 15th. This information persists between sessions and can be updated or corrected easily. The key advantages over trying to stuff everything into the LLM's context are explainability. You can actually inspect what the system knows. And updateability. If Alice's deadline changes, you update one edge in the graph rather than retraining a model. This is becoming the architecture of choice for sophisticated AI agents that need to maintain long-term memory and relationships. Let's look at some real-world scale. Google's knowledge graph is probably the most visible example of this technology in action. Launched in 2012, it now contains over 500 billion facts about more than 5 billion entities. Every time you search for a famous person, movie, or landmark and see that information panel on the right side of your results, you are seeing the knowledge graph at work. It's not just showing you web pages, it's showing you structured facts that Google has high confidence in. Data Commons is Google's more recent initiative, a public knowledge graph focused on statistical data. They've aggregated over 240 billion data points from trusted sources like the UN, CDC, and World Bank. This isn't just raw numbers. It's a structured graph of relationships between places, time periods, and measurements. Here's where it gets exciting for LLM developers. Google's newest models like DataGemma and Gemini explicitly query data commons to ground their responses in real data. Instead of hallucinating statistics, they can fetch actual charts and numbers from trusted sources. This is a glimpse of the future. LLMs that don't just generate plausible sounding text, but can back up their claims with real, traceable data from knowledge graphs. Microsoft and Meta are also heavily invested in knowledge graph technology, particularly for enterprise applications. Microsoft's GraphRAG, with version 1.0 introduced in December of 2024, is a fascinating approach to enterprise knowledge management. Here's how it works. You feed complex private documents to an LLM, which extracts entities and relationships to build a knowledge graph. Then, when someone asks questions about that content, the system can traverse the graph to make connections that might not be obvious from simple text search. They found this dramatically improves question answering on complex enterprise data because the graph structure helps the LLM connect the dots between related concepts across different documents. Microsoft also uses knowledge graphs throughout their product suite. Bing Search uses their knowledge graph for more accurate results, And Microsoft 365 uses what they call the Microsoft Graph to model relationships between users, documents, and organizational structures. Meta's involvement comes from their scale. Facebook, Instagram, and WhatsApp are essentially massive social knowledge graphs. They developed PyTorch Big Graph to handle the computational challenges of working with graphs containing billions of nodes and relationships. The lesson here is that knowledge graphs aren't just academic curiosities. They are powering some of the most sophisticated AI systems in production today. So, how do you actually build one of these? Let's get practical. For storage, you have two main options. Property graph databases like Neo4j, Amazon Neptune, and Azure Cosmos DB are probably the most developer-friendly. They store nodes and edges with properties, much like the examples we've been showing. Triple stores like Stardog and BlazeGraph use the RDF standard. Everything is stored as subject-predicate-object triples. This is more standardized, but can be less intuitive for developers coming from traditional databases. For querying, Cypher is the most popular language for property graphs. It's designed to be readable and expressive for graph patterns. SparkQL is used for RDF triple stores. The example you see here shows how natural Cypher can be. Find friends of friends becomes a pattern matching expression that reads almost like English. The typical workflow starts with defining your domain ontology. What types of entities and relationships matter for your use case? Then you import structured data from databases or CSV files and use NLP pipelines to extract additional facts from text documents. The key insight is to start small. Don't try to model everything at once. Pick a specific domain, build a prototype with a few hundred nodes, and iterate. Neo4j Sandbox is great for experimentation, and there are excellent NLP libraries like SPA-CY and Hugging Face that can help with entity extraction. Let's wrap up with why this matters for your day-to-day work as software engineers. Knowledge graphs excel in applications requiring rich relationships and semantic understanding. Search engines use them for more accurate results. Enterprise systems use them for data integration across silos. And recommendation engines use them to find non-obvious connections. The AI enhancement use cases are exploding. GraphRAG, knowledge-augmented LLMs, and persistent memory systems are all production applications you can build today. For enterprise applications, knowledge graphs shine in scenarios where you need to integrate data from multiple sources while preserving relationships, or where compliance and explainability matter. Here is the key insight. Knowledge graphs bridge the gap between raw data and semantic understanding. They make your application smarter by explicitly modeling what things mean and how they relate. This isn't just theory anymore. Google Search, Microsoft 365, Facebook's recommendation systems, These are all powered by knowledge graph technology. As AI systems become more sophisticated, the ability to maintain structured, queryable knowledge becomes increasingly valuable. My recommendation? Start experimenting. Pick a domain you understand, build a small knowledge graph, and see how it changes your thinking about data and relationships. The tools are mature, the documentation is good, and the potential applications are vast. I've included some excellent resources for diving deeper. The Stanford CS520 notes are a great academic introduction, while the Neo4j and industry blogs provide practical guidance. For hands-on learning, I'd recommend starting with Neo4j's Sandbox. It's free and lets you experiment with real graph databases. The Google and Microsoft research blogs will keep you current on the latest developments. Remember, this is a rapidly evolving field. The intersection of knowledge graphs and LLMs is particularly hot right now, so staying current with the research is valuable. That's our whirlwind tour of knowledge graphs. They're not just a database technology. They are a way of thinking about knowledge that can make your AI applications more capable, explainable, and robust. Thank you.